Section 3.1, we're going to be looking specifically at exponential functions and their graphs. And so we're sort of switching over to a different family of functions. If you read the title for Chapter 3, we're going to be looking at exponential functions and logarithmic functions, which are basically inverse functions of one another. Exponential and logarithmic functions have many applications in science. A few of the applications we'll look at are exponential growth. We look at functions regarding interest rates. We use the log function to describe the pH of acids and bases, and we also use log for to describe sound. So an exponential function is a bit different from the different types of functions that we've looked at so far. It's a simple function, however. The general form of it, as you can see here on the first page, is f of x equals a to the x. And this is probably the most distinguishing characteristic of exponential functions. We have a variable in the exponent, and here we're looking at simple functions where a is positive, a is not equal to 1. Okay, so we have what's called a base, a number, and then it's being raised to power of x. In example 1, we are supposed to pick out which functions are not exponential, or in other words, which functions do not fall into this format that we have above. So a, we have f of x equals 3 to the x power. 3 is our base. 3 is not 1, and it is positive, so a is exponential. b, g of x equals x to the third. Well, this is a polynomial. Okay, as we worked with in Chapter 2, our base is the x variable, not a number as in the format above. So this would not be an exponential function. C, we have a base raised to the x power. 2.75 is our base. It's greater than 0 and it's not equal to 1, so h of x is exponential. I of x, we have 4/7 raised to the x power. I is exponential. 4/7 is definitely not equal to 1, and it is positive. 4/7 is less than 1, but we just simply don't want it to be equal to 1. It can be less than 1. E, we have j of x equals x to the x. This is not exponential. We want a number as our base, not an expression involving a variable. E, k of x is 3x minus 1 divided by x plus 4 to the third power. This is also not exponential. We want our base to be a number only, not an expression involving a variable. Notice remark 1 says exponential functions can also have fractions, or in other words, they can have negative exponents. And remember from your exponential rules from intro algebra, if we have 2 to the negative 1 power, that is the same as 1 over 2. We simply take the number with the negative exponent and we swap sides of the fraction. Okay, so this also applies to the bases of exponential functions. So b to the negative x, if we want to get rid of the negative in front of our exponent, then we simply sort of as an intermediate step, we could write b to the negative x as, let's see, 1 over or even better, b to the negative 1 times x, and then we can sort of isolate b to the negative 1 and split these up using the power rule, and then b to the negative 1, with b just simply being a number, can be written as the fraction 1 over b. And here's what we have from our workbook. Okay, and so 1 over b is, they're simply saying that this is just a number as a was. So let's look at example 2. We have 3 to the negative x equal 1 over 3 to the x. And here they're not really asking us to do anything. They're just pointing out several versions of the exponential function where it's expressed with a negative exponent. Here we have 0.25 to the negative x. It can be rewritten with a positive x. However, we take the 0.25 and put it on the bottom of a fraction with 1 on top, and then 1 divided by 0.25 gives us 4. All of these are equivalent versions of the same exponential function. Here on the bottom, capital F of x, we have 2/3 to the negative x. If for whatever reason we want to get rid of the negative sign in front of our exponent, then we simply take the reciprocal of the fraction. Again, we could look at this as 2/3 to the negative 1 raised to the positive x power. Okay, we're just transferring the negative to the number, and then the negative 1 simply means that we take 2/3 and flip it. We want the reciprocal of 2/3, which is 3 over 2. And this is exactly what they're showing you here in the workbook. Okay, more functions of exponential forms. We don't simply just have to have x as our exponent. We can have expressions that are based on x. So for instance, we have a new format of an exponential function, a number raised to an expression depending on x, u of x. Alright, however, u of x still has to be a function itself. A has to be positive, and we do not want a to equal 1. Alright, if we did have a equal 1, suppose we had f of x equals 1 to the x power. Well, no matter what we put in here for x, we'll always get 1. So we could put 1 to the 1/2, which is the square root of 1. Well, we get 1. We could have 1 to the 0. Anything raised to the 0 power is 1. We could have 1 to the 30th power. No matter how many times we multiply 1 by itself, we still end up with a 1. So this is why we, and 1 is not exponential. 1 to the x is not an exponential function. This would just be a flat horizontal line if you were to graph it. And as you'll see here in a minute, exponential graphs, functions have curved graphs. So example 1, just really pointing out some exponential functions of this form, where we don't have just an x as our exponent. For instance, little f of x has 2x minus 1 as the exponent. Okay, the base equals 3. The exponent equals 2x minus 1. For g of x, the base equals 2, and our exponent equals x squared minus 5. And our exponents are both functions. X squared minus 5, this is a parabola. 2x minus 1 is a linear function. So both of these fulfill the condition that u of x is a function. They want us to evaluate this exponential function at 1. So we do the same as we always have. We replace the x with the 1. And remember, all of this is an exponent, so we want to calculate that so that we know how many times to take 3 and multiply it. 2 times 1 minus 1 would boil down to a 1, so what we have is 3 to the first power, and we'd end up with 3. F of 1 equals 3. G of 3, we have 2 raised to the power of x squared minus 5. So we plug 3 into the exponent and we square it. This 3, the square, minus 5, this is all inside of the superscript. Okay, we need to calculate this and then write the outcome as an exponent. 3 squared is 9. If we subtract 5, we would get 2 to the 4th power. So we take 2 and multiply it by itself 4 times. And in that case, we'd get a 16. So g of 3 is 16. So when you're dealing with exponential functions that have functions in the exponent, then make sure you keep all of those calculations written inside of the superscript. Alright, so whenever you run into a function that you're unfamiliar with in any math class, one way to approach it to get an idea as to what the function is going to look like graphically is to just plot a table of values, and that's exactly what we have here. We're going to plot f and g for x equal -3, -2, -1, 0, 1, 2, and 3, just to get an idea as to what these two functions look like. So let's write f we have f of x. We're going to do one at a time, so I want to fill out this first row in my table, and my first x value is -3, so I'll have to do each of these separately. F of -3 is 2 to the -3rd power. Okay, and with a negative exponent, I can take the base to the bottom, 2, and write that as a positive exponent now. So writing the 2 in the denominator causes the exponent to now become a positive 3. So this is 1/8. 2 to the 3rd is 8. 1/8. The next x value that I want to plug into little f is a -2. Okay, to get a good idea as to what this function looks like, we need to plot several points along the curve. So here we have 2. This is the base. Okay, no matter what the x is, x value, this is our base, 2. And our exponent is the x. And that's probably something that'll take a little getting used to. So this page should be pretty helpful if you actually walk through and calculate each of the entries in the table. With f of negative 2, we have a 2 raised to the negative 2 power. To get rid of the negative, we simply write the base 2 in the denominator, and then the 2 of the exponent becomes positive. 2 squared is 4. So f of negative 2 is a 1/4. So from negative 3 to negative 2, we have our y value increases. The next value we have is f of negative 1. If we write 2 on the bottom, our base, then the negative 1 becomes a positive 1, which can be interpreted as simply a 1/2. Next we have f of 0, and so we write 2 to the 0 power, and anything raised to the 0 power is 1. F of 1 equals 2 to the first power. Anything raised to the first power is just itself. F of 2 equals 2 squared. 2 squared is 4. F of 3 equals 2 to the third power, which equals 8. So our last entries in the f of x row are 4 and 8. Before I plot f of x, I'll go ahead and use this space. I'll erase this, and I'll use that space to calculate g of x. We have same base, but now we have a negative x as an exponent. And we have a different label for this function, g, and so we want to calculate the outputs for g of x using negative 3, negative 2, and so on. G of negative 3 would be a 2. This negative comes from the function, and then I'm going to insert another negative from the input, so I have a minus minus 3 in the exponent. Minus minus 3 is a superscript here, so I have 2 to the positive 3, which is an 8. Now I calculate g of negative 2, and so I have a 2 to the minus minus 2, which is 2 squared, which is 4. Now we calculate g of negative 1. We get 2 to the minus minus 1, which is 2 to the first power, equals 2. And so we've sort of flipped our values with respect to the y-axis. The next x value that we want to input into g is 0. We have 2 to the negative 0, which is the equivalent of just 2 to the 0. The negative doesn't affect the 0, and so anything raised to the 0 power is 1, so we should write 1 here, just like we did for f of x. G of 1 equals 2 to the minus 1, which can be written as 1 over 2 to the positive 1, The exponent now becomes positive because I've moved the base from the numerator to the denominator, and this can be just written as a 1/2. G of 2 would be 2 raised to the negative 2 power, which is 1 over 2 squared, getting 1/4 for G of 2. And then finally G of 3 would be written as G to the negative 3rd power, or 2 to the negative 3rd power, or 1 over 2 to the positive 3rd power, ending up with 1/8. One thing that we've seen before with numbers being reversed was when we took f of x and we simply put a negative in front of f of x, and doing that takes the values of the function f of x. Okay, try to jog your memory here. So let's say that f of x is this function. Then placing a negative in front of f of x would result in a similar function where the values would be flipped across the x-axis, and it would look something like that. Well, this isn't the case for our f and our g. What's happened here is g of x is simply f of x with a negative x placed inside of its argument. And if we do that, we would write f of x, which is 2 to the x, and I leave a blank for the x, and now we place a negative x inside of it, which is the same thing as 2 to the negative x. It's g of x. Doing this with functions, any function, will, instead of flipping the values across the x-axis, it will mirror the values across the y-axis. So for instance, if f of x looked like this, then g of x, which is f of x with a negative x inserted, would look like this. It would mirror across the y-axis. So there's a difference between placing a negative inside of the argument versus placing a negative outside of the function notation. So what we'll do now is we'll just graph our values in our table and figure out what f of x and g of x look like. We'll get an idea as to what exponential functions look like. X equals negative 3, which is about here. And let's see, we have numbers as small as 1/8 and as big as 8. So let's see, I have to be careful with my y scale. 1, 2, 3, 4. 1, 2, 3, 4. Let's see, I want to make sure I have enough for 8. I'll use 4 units for 1. 1, 2, 3, 4. That's 2. 1, 2, 3, 4. 1, 2, 3, 4. So we have 3, 4, 5, 6, 7, and 8 would be 1, 2, 3, 4. So right about there. Graphing f of x in red, I have negative 3 and an 8. I've divided my ones on my y-axis up into 4 units, and an 1/8 would be half of a fourth, so I'd have my point fall right about there. Negative 3 and 1/8. Negative 2 and a fourth would fall right along that first tick mark on the y-axis. Negative 1 1/2, 2 tick marks up. 0 and 1, 1 and 2, 2 and 4. So our function is really starting to shoot up now. And then finally 3, 2, 8. So every time we move over 1 on our x-axis, we multiply the previous output by 2. Connecting all of the dots with a curved line, we get an idea as to what an exponential function can look like. So this increases from left to right. How about g of x? I'll sketch it in green. And here we just reverse our numbers. At negative 3 we go to 8, which is up here. And at negative 2 I drop down to 4. Negative 1 would be a half. Oh, I'm sorry, negative 1 would be a 2 for g of x. I glanced at the f of x value. 0 would be 1. So they would cross right here on the y-axis and overlap. G of x at 1 would be a half. 2 would be a fourth, and then 3 would be an eighth. Pretty close to the x-axis. And so you can see that they're mirror images of each other with respect to the y-axis. And that's simply because we placed a negative x inside of the argument of f of x to create g of x. So they're mirror images of one another. Alright, so exponential functions can drop off really quick and decrease from left to right, or they can start on the left and increase pretty rapidly. But if we stick with the strict format to where f of x equals a to the x, then we're going to get one of these two functions. It's either going to decrease or it's going to increase depending on what a is. If a is less than 1, then we get this decreasing behavior. If a is greater than 1, then we have this increasing behavior. And we also, for all of the functions that fall into this form, we also have a horizontal asymptote here at x equals 0. Or I'm sorry, y equals 0. These functions never cross the x-axis. Alright, so now you should have a pretty good idea as to what these exponential functions can turn out to look like on your graphs. Exercise 1, it says repeat the above example for functions f of x equals 3 of x and 3 to the negative x, and then we also want to sketch those on the graph above as well. I am going to take a shortcut, and I'm going to use my calculator to generate these tables. So here we go. I will use y1 for f of x, and I'll use y2 for g of x. And down here on exercise 1 it says we want f of x to be 3 to the x. And then g of x is now going to be 3 to the negative x. Make sure you use the negative sign and not the subtract sign. Negative is down here with the decimal point and the numbers. It's the white button. Enter. And I will go to my table. And our table in the workbook ranges from a negative 3 to 3. Alright, so here we see we've got 0.3. The decimals are a little hard to interpret, but I'll show you the values for f of x. I'll work these out in the workbook. And then g of x is once again just f of x with a negative x inserted as the argument. So g of x equals f of x flipped across the y-axis. Symmetric about y-axis. Alright. And that's when the two are graphed together. Okay, these functions individually are not symmetric about the y-axis. I think you get the idea. Okay, f of x, we want to run from negative 3 to 3. So f of x is 3 to the x. Inserting a negative 3 for x would give us 3 to the negative 3, and we could write it as 1 over 3 to the third, which is 1 over 27. Very small number. I can calculate that with my calculator, and it's already calculated in the table. We're going to get a 0.03704, but just to prove to you that this is where that value comes from, I'll calculate it on the home screen. 0.037037037. The table has merely rounded the number. Okay, so it's really small, 0.037 is what I'll write in our table. F of negative 2 would be 1 over 3 to the second power, or 1 over 9. And from the table we see that 1/9 is 0.11111, easily verified with your calculator. Still very small. F of negative 1 would be 3 to the negative 1. or 1 over 3 to the positive 1, which is the same as 1/3. And so you see the 0.333. Probably pretty familiar with this fraction. 1/3. 0.3 with a bar. We could say the same for the rest of these. For the first one, 0.37 just repeats. 1 repeats for f of -2. 3 repeats for f of -1. Now we have f of 0. Anything raised to the 0 power is 1. F of 1 would just simply be 3 to the first power, which is 3. And then we have 3 squared, which is 9, and then 3 to the third, which would be 27. And this is exactly what we have in our y1 column from our calculator. And then we see that y2, g of x, 3 to the negative x, just simply reverses the outputs that we have in our table. So g of -3 would be 27, g of -2 would be 9, 3, 1, 0.33, 0.111, 0.037. I'll plot f of x in the red at -3, very small number, -2, small number still. And if I use my values of every 4 equals 1 unit on the y-axis, then you'll see that this 3 to the x is going to shoot up a lot faster than the previous function we sketched, 2 to the x. -1 is a third. We still get 1 for our y-intercept. And now our new f of x really takes off. At 1 we have 1, 2, 3. Let me see. 1, 2, 3, 4. 1, 2, 3, 4. 2 we have 9, which is way up here past the scale of my y-axis, whereas my previous f of x was, let's see, 8 was right here, and so 9 would actually be inside of my table. I'll go ahead and finish f of x equals 3 to the x. Alright, and graphically this isn't doing a lot of justice in comparison to the function 2 to the x. And I don't want my red curve to drop down and touch my x-axis, so I'll go back and clean that up a little bit. Alright, we'll look at the calculator, the graph, and here you should see our f of x curve right there. And so, as you would expect from the initial f of x and g of x, our g of x of 3 to the negative x is going to be rotated around the y-axis. Here is our g of x in the green, and f of x is in the red. So we have it plotted. Now I'll just go back and plot g of x here we have 2 is 0.11, really close to the x-axis. So close I really can't differentiate between these two coordinates. Then as we get closer to 0, 1 is a third. We cross through y equal 1 on the y-axis. Then from right to left, 3 to the negative 1 would be 3. I just simply mirrored this point. And then for negative 2, I would mirror that point over here on the other side of the y-axis. And then once again at negative 3, it would shoot way up here past the limits of my graph. And I'll do the best I can to graph a line through those points. That looks a little bit too straight. Let's see. I should have had a little bit more curve in there. Not sure why that didn't work out, but calculator gives you a lot better picture. G of x decreases rapidly and then it flattens out along the x-axis. F of x is initially from left to right, pretty flat, and then it spikes once we hit the y-axis. Increases very rapidly. Alright, one last thing I want to do with the calculator is to compare three to the x and 2 to the x. Alright, f of x equal 2 to the x will be in green. It doesn't increase as rapidly as 3 to the x. And then f of x in the red equal 3 to the x power is much steeper. Okay, so that should give you some idea as to what happens to the functions when the bases change. If we increase the base and we have positive x as our exponent, then when the function starts to increase, it gets a lot steeper quicker. Page 73, we have a special exponential function, e. You should notice the E button on your calculator. It is located, let's see, right here on the LN button. We have to hit second first, and I'll go back to my Y editor, clear out these previous functions. We have to hit second first, and then the LN button, and you see we get an E, and then we can enter x as the exponent, and we'll go to the table of our calculator and enter in these values for the graph. I'll enter these top three, and then I'll go here and calculate in the workbook the bottom three. Alright, so what is the value of E? Well, you could compute that by simply putting the 1 into this natural exponential function. So e to the 1 turns out to be 2.71 approximately. And if you read the workbook, that's the value that's given for E. E equals 2.71, and it's an irrational number, so these digits never stop and they never repeat. E to the 2, or f of 2, equals e to the 2, and we can read that from our table here. E to the 2 is 7.39 if I round it. F of 3 equals e to the 3rd, and so we read our table at x equals 3, and we get a value of 20.1. So for f of negative 3, we would have e to the negative 3, and probably difficult to raise 2.71 with endless digits to the 3rd power, okay, the negative 3rd power. So to calculate these outputs, we'll use our calculator again. And so if you didn't go to the table, you could simply go to the home screen, go to second, and hit the LN button. The e to the x, or the e, is right here above the LN in blue. And now we type negative 3 and hit enter, and we get 0.049787. Alright, we're going to round it at some point, and so I'll just simply write 0.050 for f of negative 3. F of negative 2 will be e to the negative 2. To compute that with the calculator, second ln negative 2, make sure you hit the negative button, enter, 0.135. 0.135. And f of negative 1 will be e to the negative 1, or you can write 1 over e. So second ln to the negative 1, and then 1 over e, enter. Oh, I need to enter the 1. You're going to see that we get the same thing. Okay, 0.3678. I'll call it a 0.368. So there we go. We've finished our table. Except for x equals 0, which is easy because even if we raise this irrational number to the 0 power, we're still just going to get 1. So each of the 0 is 1. Let us graph these values and get an idea as to what e to the x looks like. Our largest output is 20, and this is going to be a little difficult to graph here. I'll use, let's see, I'll use every 2 tick marks as 1, 1, 2, 3, 4, 5, and we're actually going to go past 20, so I'll back up and I'll just use a 1-to-1 scale where this equals 1. Okay, and I have 1, 2, 3, 4, 5, 6, 10. So this is 10, and so 20 is going to be somewhere in here. I'll call that 20, just so that we can graph the full range of this table. So at -3, I have a number that's much smaller than 1. I'll just plot a point right here along the x-axis. And moving over 1 unit to the right isn't going to change that much. It's still really close to the x-axis. -1 gives me a slightly bigger number. I've got about a third now, but I'm still really close. And then at 0, I finally jump up to 1. At x equal 1, I have 3. So 2, 3, and then x equal 2, I've got 7. That right about there. And then x equal 3, I jump up here to 20. Alright, so FYI, if I were to graph, let's say g of x equal 3 to the x, and then I was to graph another one, let's say h of x equal 2 to the x. This won't be accurate, but I just want to point out that if I graph 2 to the x, it would be pretty close to this curve. It would still pass through 1. However, it would be slightly underneath this curve for e to the x, because e is 2.71 and 2 is less than that. So if I have a smaller base, then the exponential function doesn't increase as rapidly. On the other hand, if I were to graph 3 to the x, it would still pass through 1, and it would fall just above e to the x, probably a little bit closer, but 3 is bigger than 2.71, and so it would increase more rapidly than e to the x. And we already see that it pretty much looks like an exponential function. We already have the natural exponential entered into our y editor. If we hit graph, it just simply confirms that it has an exponential form to it. Okay. So at the bottom of the page, we list some properties of the exponential functions, and that includes the natural exponential function e to the x. Any of the exponential functions that we've talked about so far. The domain is all real numbers, and the range is 0, infinity. Okay, because we said earlier that it doesn't touch the x-axis, and x-axis is y equals 0. There is a horizontal asymptote at y equals 0, so it's not going to touch the x-axis or drop below it. So domain is all real numbers. It spans the entire x-axis, and then it only occupies the space above the x-axis for the y-axis. 0 to infinity is the range. Y-intercept is 0, 1. As we saw, all of the exponential functions we graphed crossed through y equal 1, and since we cannot cross the x-axis, there is no x-intercept. 3, we've already stated this one, horizontal asymptote, the x-axis, or in other words, y equals 0. There are no vertical asymptotes. The domain is not bounded or restricted from any values. No vertical asymptotes. 4. The function is increasing if a is greater than 1. So you need to think 2 to the x. And then decreasing for a between 0 and 1. And one such function was 2 to the negative x. But here a is not 2. Okay, you need to rearrange this function in the form of a positive x. And so doing that, you would have 1/2 associating the negative part of the exponent with the 2. You would rewrite the 2 as 1/2 with a positive x. And so here we have an a that is less than 1 and greater than 0. And so this is decreasing for all x in the domain. If a is greater than 1, then the function is increasing for all x in the domain. 5. Exponential functions are 1-to-1. And therefore we can use these properties, or this property, to solve equations that involve exponential functions. So for instance, if I had 2 to the 3x, and then I also had 2 to the let's say x plus 9 or 8, doesn't matter, then to solve this I could say, well, the bases are the same, 2 and 2 on both sides. I could drop the bases, and with it written this way, 3x and x plus 8 are written as exponents. But when I drop the 2's, with the bases equal, I can bring the 3x down and set that equal to the other exponent. In other words, the exponents are equal if the bases are the same. And we're dealing with an equation of this form. Then I can write out this and solve for x. So pretty handy property. And again, that's because exponential function is 1-to-1. It passes the horizontal line test. So example 5 says solve each exponential equation both algebraically and graphically. Alright, from property 6 above, and I'll double check that and make sure, yep, it's property 6. It says that if the bases are the same, then we just set the exponents equal. So we have an expression for this exponent, 3x minus 7, and that must be equal to x plus 5. And pretty simple to solve in this case. Subtract x from both sides, we get 2x minus 7 equals 5. The x is canceled on the right. Add 7 to both sides. We get 2x equals 12. Divide by 2. And so x must be equal to 6 in order for these two exponential expressions to be equal. So definitely makes a complicated situation way more simple. Just check the bases and make sure they're the same. If they are, then the exponents, or the expressions for the exponents, have to be equal. And we end up with equations that we've solved several times. This one has a squared x, and so it's quadratic. We need to shift everything over to the one side. If I add the 4 both sides, then I would now have an x squared plus 2 equal 3x. And now if I move the 3x to the left, I end up with our standard quadratic or general quadratic equation. Luckily I can factor it. Minus 2 minus 1. And so we get x equal 2 and x equal 1. For D, what we have here is just everything's moved to one side. Okay, and there's a few more things involved that we'll need to clean up. If I just simply take one of these expressions, this one's subtracted, so if I just move that to the right, I can just add this entire x plus 2 times e to the x to both sides. I would get the following equation. And now I could simply divide both sides by e to the x. No need to use property 6 here. And the e to the x's would cancel. And I don't have to worry about e to the x being 0. Okay, because the range doesn't include 0. The range only includes positive values. So e to the x will never be 0. And I have 3x equals x plus 2 once the e to the x is gone. Subtract x from both sides. Gives me 2x equals 2. And now if I divide by 2, I see that x equals 1. And so I can always double check this. Just plug the 1. It works just like any other equation. Plug your value for x back into the original equation. We get 3 times 1 e to the 1 minus 1 plus 2 e to the 1, and we want that to work out to be 0. 3 times 1 is 3 e. 1 plus 2 is 3, and e to the 1 is just e as it was over here, and so 3e minus 3e does equal 0, so our solution checks out. So even though an exponential function was involved with this one, we don't always have to use the property above, property 6. Applications, our first one, investment. A few different ways to calculate interest. Here is simple interest. The interest is the principal times the rate times the time. Okay. Then here we have the amount that we have in the account at any one time in the future once we put our money into it. So P is how much we put into the account initially, the principal. A is the amount after T years. So to get the amount at some future date, I simply take the original amount that I place in the account P, and I add the interest that it's accumulated over a number of years. Written a different way, P again plus the formula that was presented over here to the left. Instead of writing I write PRT. This can be rearranged over here on the right. A equals, factor out the P, and then we have 1 plus RT. Alright, so any one of these forms is okay. Some may be more useful depending on the situation. Alright, and R is usually expressed as a percentage. which when you insert into the formula you want to write as a decimal. T is in years, and then in the end I, P, and A are expressed in dollar amounts. And here we see that there's three different types of interest calculation: simple, which is expressed here; compound; and continuous, which we'll look at here in a minute. Example 6 reads, suppose $12,000 is deposited into a savings account with an annual interest rate of 2.5%. Calculate the amount of money in the account at the end of the 6th year if simple interest is used. So A is the amount in the account, amount of money. And I will go with the formula above, P times 1 plus R T. Okay, P, because that's how much we started out with, so we definitely have P, the $12,000 in there, and then P times RT is the interest formula. So we're going to add the interest that we've earned on top of what we put in there initially. Alright, really just a matter of putting the numbers in the right places. Okay, $12,000 was deposited initially. So $12,000 is our P, our principal. 2.5 is our rate. And so in the formula, I enter 0.025. And then for T, we have 6 years. The 6 or 6 years. And at this point it is calculator time. $12,000 times 1 plus 0.025 times 6, parentheses, enter, $13,800. So what about compound interest? In this method, a year is divided into k shorter periods. Interest is calculated not only on the initial principal, but also the accumulated interest of prior periods. Alright. So suppose P dollars are deposited into the account earning interest at an annual rate of R, compounded k times a year. If A is the amount in the account after T years, then it can be shown that, alright, new formulas. So here we have the amount, and if we compare that to the simple interest, the previous formula, we still have P in front of a set of parentheses. However, T is now located on the outside as an exponent, along with K, which is however many times we're going to divide up a month, basically, or not a month, but divide up a year. Alright, so K could be 12 if we compound interest monthly. K could be 2 if it's compounded semi-annually, and so on and so forth. And now on the inside, instead of having R, the rate, times the time, we have R divided up into the K periods. So for instance, if my annual interest rate was 12%, R equals 12%. As a decimal, that would be 0.12. And so for each month, we would have a new rate. I'll say R month. At the end of the year, we would pay the full 12%, but each month we would have a rate of 0.12 divided by 12 for 12 months in a year. And so for every month we would calculate an interest, or accumulate an interest of 0.01. And that's what the R divided by K represents there. So let's actually use these formulas that we're given. Monthly, K equals 12. Weekly, there's 52 weeks in a year, so K equals 52. And daily is 365. Same problem as before. 12,000. The annual interest rate is still 2.5%, and we want to know how much interest, or what the amount is at the end of the 6 years. So A equals P times 1 plus, now our rate is going to be divided by 12, divided up equally among the months, and then we have a KT as our exponent, so 12 times 6 years. So this is just how many times we're going to compound the interest. There's 12 months in a year, 6 years, 6 times 12. And our P I should have replaced with a 12,000. So here's what we need to enter into our calculator. 1 plus 0.025 divided by 12 to the 6 times 12 is 60 plus 12 is 72. $12,000 times 1 plus, and I'm going to put this fraction in parentheses, 0.025 divided by 12 to the 72nd power. 13,939, or I could say 40 if I round it to the nearest whole. 13,940. So in the previous simple interest example, let's see, how much did we earn? I think it was 13,800. 12,000 times 1 plus 0.025 times 6. Yeah, 13,800. So with monthly compounded interest, we earn an extra $140. So we'd be better off finding a monthly compounded savings account. Weekly, we now divide our interest rate by 52. However, we have 52 times 6 compounding periods. Okay, I will just simply take the previous expression that I wrote for compound interest, bring it down and change the 12 to a 52, and for my exponent I will write 52 times 6 instead of calculating it in my head, and here we go. We get 13,942 if I round it. So compounding it weekly instead of monthly has now only earned me $2 more during the same 6-year period. So I suppose it really wouldn't be worth the effort to look around for a weekly compounded savings account. One last formula for the daily compounded interest. We now divide by 365, and for KT we write 365 times 6. Alright. Enter in this into my calculator one more time, 12,000. Be careful and use as many parentheses as you need. I place a parenthesis around the fraction inside of the parentheses, the 0.025 divided by 365. And now I have an exponent of 365 times 6. Enter. And for weekly I had a 0.5 when I rounded. For daily I now have a 0.9, and so if I round to the nearest whole I get the same thing as I did for weekly, 942. So as far as interest earned, you could definitely argue that it's worth it to switch from a simple interest to compounded monthly, but you're really just splitting hairs between monthly, weekly, and daily. Not really that big of a difference, approximately $2. Example 8, how much should be invested in an account now in order to have $10,000 in 5 years if the account pays 3% annual interest compounded quarterly, which is going to give us a K of 4 times a year. You could use the same formula that we just did, but A is now going to be 10,000, and the P we don't know. Okay, let me write the full formula out. A equals P times 1 plus R over K to the KT. So we would have 10,000 equals P, and we want to solve for P. The rate is, let's see, 3%, so we would write 0.03 for R, and K is 4 for compounded quarterly. And then we have another factor, K, it appears in the exponent, times the years. There's 5 years, so we're going to compound 20 times. This works out to be P. Let's call up our calculator to calculate the part with the parentheses. 1 plus 0.03 divided by 4. May not need the parentheses around the fraction. I'll try to get away with it. Then we want to raise that to the 20th power. Oh, but I didn't put my exponent in. 20. Enter. Alright. 1.16. So here's our equation. 10,000 equals P times 1.16. If we just simply divide both sides by 1.16, 1.16 cancels out, and so P would equal 10,000 divided by 1.16. $8,620 would be our principal. We'd have to invest $8,620 into an account with 3% annual interest compounded quarterly in order to have $10,000 after 5 years. How about continuous compounding? This, you could argue, is a lot easier to memorize than the previous compounding formulas. We simply have A equals P times the natural exponential function with the exponent of rate times time. Okay. You can get this alternate form of the equation by simply taking this one above and writing e to the RT, dividing both sides by e to the RT. If we want to solve for p, so on the right, the e to the RT cancels out, and we don't get in trouble in the sense of dividing by 0, because exponential function can never equal 0. And here we are with the e to the RT on the bottom, and this would become a times e to the negative RT. If we move the e to the top in the numerator, we can put a negative in front of it, and then on the right we just have our principal, which is the same exact formula given here. So you really only need to memorize one formula and then just know how to apply algebra. So example 9, repeat example 7 above with continuous compounding and compare your results with those in example 7. Can you draw a conclusion? Alright, let's see, example 7, what was that? $12,000, 2.5, and 6. Plugging those numbers into my continuous compounding formula, I get e to the 0.025 times 6. Way easier to memorize, and you're gonna find out that it gives you approximately the same amount as we did before with the compounding formulas, the monthly, the weekly, the daily. So $12,000 in my calculator. Second LN button for the natural exponential e, 0.025 times 6, enter, 13,942. So almost identical to the amount that we received from calculating daily compounded interest. Approximately daily compound interest, and it's only $2 away from the monthly interest and $142 away from simple interest. Alright, B, how much should you how much should be invested in an account now in order to have $10,000 in 5 years with compounded continuous interest? Compare the result from example 8 above. Let's see, A equals P e to the RT. So now we have our amount that we want. We don't know the principal. The rate is 3%, so for R I have 0.03, and I multiply by, let's see, 5 years. What is E to the 0.03 times 5, enter, 1.16. So in other words, I can divide both sides by 1.16 because e to the 0.03 times 5 is 1.16. I just calculated it. This cancels, and I'm going to get the same value that I did before for example 8. I don't remember what that was, but bring up my calculator. 10,000 divided by 1.16, enter, 8,620. So if you look back at your notes on the previous page, these two values were identical after we rounded. C, graphical solution only. A mutual fund is paying 2.5% compounded continuously. If you decide to invest $25,000 in this fund today, approximately how long will it take for your money to double? Alright, so we have our formula, A equals P e to the RT, and it did say continuously. We want to invest $25,000. We have an interest of 0.025, and the time is, well, we don't know the time. That's what we're looking for. But we do know that we want to double our money, our initial investment of $25,000 in that amount of time. So if we double $25,000, our amount should be $50,000. To solve for T, we divide both sides by 25,000. And so we run into a problem. We don't know how to get this T by itself, but we'll learn how to do this algebraically in the upcoming sections. So if we follow instructions and do this graphically, we could enter in y equals, let's see, we want our exponential function to equal 2, to output 2. So if I put into my y editor e to the 0.025x with x in our calculator in the place of t, and I graph it, okay, I want an output of 2, so I'll just simply hit trace and enter, let's say 20 years. Take a guess. Well, it's not on my calculator, so I will zoom out and I'll zoom out again. Well, hold on. Let's try to be smarter about this. We can go to our x values, which is our time. We have x max is 40, and we want an output of 2. So I'll just simply put 3 here and enter, and we'll see that where that gets us with our graph. So let's trace. And if we hit trace, we're on our curve, and we want this to give us a y of 2. I'm at x equal 20, so the time 20 years is not enough. I keep moving over to the right, and there we go. Okay. If I scroll over to the right with my arrow key, I can find the output that I want, and according to this equation it's 2. That the calculator tells me that I need to wait 28 years in order to double my money, and the 2 is for doubling our money. So we can write T is approximately 28 years. You could have graphed this initial PE to the RT if you wanted to, and then you would have looked for the output of 50,000. So let me run back and do that. And you'll get the same 28 years either way you go. We just have to enter a different function into our y editor. So I will insert 25,000 in front of it, hit enter, graph. Of course we don't see our curve anymore because we've went from a value of looking for a value of 2 for y, and now we're looking for a value of 25,000. So I'll go back to my y max and I'll put in 30,000, just a little over 25,000. I'll hit graph. Okay, well actually we're looking for 50,000. I'm sorry, 50,000 in our window. We want to double our money, so I will put in 60,000, enter, graph it, and there we go. It looks a lot like the curve that we looked at initially. Hit trace, x equal 20 years. We're only at $41,000, not quite double. We arrow over to the right until we hit 50,000, and 49,917 is closer than 50,451. So we'll read our x value and we get 27.65, which if we round it to the nearest year, we would still have 28 years.